In this second video on elliptic curves, we're going to take the associative binary operation that we learned about in the first video and see how we can form a group out of the points that lie on elliptic curves. One reason that we really want to do this is that elliptic curves are used in a lot of different public key cryptosystems, and perhaps the most famous example of this is Bitcoin. Bitcoin actually uses elliptic curves in their digital signature algorithm, and so it's nice to know that this is being used in a very modern day atmosphere. But in order to use the elliptic curves as they are used for cryptography, we're going to need to work with the points on elliptic curve working modulo some prime number. And typically, when we see this in practice, it's going to be a very large prime number. In the examples that we use in these slides, we're going to use a small prime number for ease of computation. But now when we're working with elliptic curves modulo prime number, we're going to have to make a slight change to that technical requirement that we saw in the first set of videos. If you'll recall, in the first set of videos, we had these depressed cubic elliptic curves of the form y squared is x cubed plus ax plus b. And we had this technical requirement that the quantity 4a cubed plus 27b squared could not be equal to 0. That requirement is now going to change to become 4a cubed plus 27b squared cannot be congruent to 0 modulo the prime that you're working. But the very first thing we need to do now, we can't graph these elliptic curves anymore, at least not till the end of the video. We need to figure out how we're going to determine the points that lie on this elliptic curve modulo this prime number. So what we're going to be doing is we're going to be using the same elliptic curve from the first video, y squared is x cubed minus x plus 1. And we're going to be looking at working on this curve modulo 5, very small prime number. And we need to construct the set of points that live on this elliptic curve. So the way we do this is in two steps. The first thing we do is we consider the left-hand side of the equation, the y squared part, and we create a table that tells us what are all the different possible values for y squared working modulo 5. So we just make this list of inputs, y's right here, 0 through 4, and their outputs, not what the actual square is, but what that value is when we mod by 5. So you're going along and you have 0, 1, and 2 working as they always have. But when you take 3 and square it, you get the number 9, but we only really care about 9 working modulo 5, and that remainder becomes a 4. And then a similar thing happens with the 4. You square it, you get 16, and when you're working modulo 5, that turns into a 1. So you get this nice table of values, and it tells you these are the squares of all the different inputs if we're working modulo 5, and determines, again, the left-hand side of this equation. Note that this is sort of interesting. If you're looking at a value of y squared and you're looking at 4, just as it always has been, 2 is a square root of 4. However, something interesting happens here, and something that doesn't happen in the integers does happen when we're working mod 5, which is that 3 now becomes a square root of 4. It seems a little strange here, but something that we'll see later, 3 is really acting like a negative 2 in this particular number system, and so it isn't quite as weird as it seems, but it seems strange to say naturally 3 is the square root of 4. Now the next step is, let's take a look at the right-hand side of this equation, and just as we did with the left-hand side, let's make a little table. So we have the values, all the different possible x values that we could get anywhere up 0 through 4, the elements of z mod 5z, and what they evaluate to when we plug them into x cubed minus x plus 1. Again, we do that computation and then take the answer modulo 5. So some of these lower values work just as they should. If you want to do an example with something like 2, if we were looking at 2 cubed, which is 8, minus 2, which is 6, plus 1, we would end up with a value of 7, and 7 is not what we put in the table, but rather 7 modulo 5, which is 2, and a similar computation can be done for the remaining entries here. So now we've created tables for the left-hand side and tables for the right-hand side. The way we're going to determine the points on the elliptic curve is to put these things together and play a little matching game. So for example, we're going to say when I plug in an x value of 0, the right-hand side of this equation becomes the number 1. And then to figure out what points go on the curve, we say, well, what different y values would square to give me 1? Those will be my pairs x, y. My input will be 0, and my output will be the y values that square to the same output right here. So if you take a look here, when I plug in 0 for x, the right-hand side evaluates to 1, and I would have also gotten a 1 if I would have taken 1 and squared it, or likewise 4 and squared it, working mod 5. And so the first 2 points that I throw onto my elliptic curve are the points 0, 1 and 0, 4. And my input x was 0 to get this output of 1, and inputs for y of 1 or 4 would have given me that same output in the column over here. So 0, 1, 0, 4. And what I'm going to do is I'm going to go through and play that game for each one of my different inputs x. And when I've exhausted this column of the table, I'll be done adding points to my elliptic curve. So the very next thing I do is the same trick for 1. It happens to have the same output. So when my input x is 1, these two x coordinates right here, x cubed minus x plus 1 mod 5 evaluates to 1. And the y values that would have that same output are 1 and 4. So the pairs 1, 1 and 1, 4 go into this list. 3, 0 is a somewhat unique point because when I plug in an x value of 3, I get an output of 0. And 0 can only be acquired in the y squared column by putting in y value of 0. So the point 3, 0 comes to the list, but it doesn't really get a pair since I only see this output of 0 one time. And the input of 4 is the same as it was for each of these 0 and 1 columns. When I plug in 4 for x, I get a 1 in the output here, and both a y value of 1 and 4 would give me that result. Notice that I don't have any points on the elliptic curve with an x value of 2, because when I plug 2 into this right-hand side of the equation here, the output that I get for x cubed minus x plus 1 is 2, but there aren't any y values that square to 2. And so there's nothing I could put in this second coordinate if I had a 2 in the first coordinate, and so I omit this as a possible x value altogether. And that's basically all I do to create this point with one exception. Remember that I do have to add the point infinity in order to make this set E a group. My infinity is useful to me here, and so I have to add that theoretical point, which doesn't really have a physical manifestation, but is going to be needed in order to make E into a group. I want to take a brief pause here to show you how you could have gone about doing this process if you're skilled in Mathematica. So if I pull up Mathematica and just initialize a little cell here, what I've done in Mathematica is created tables, just as I did in the PowerPoint presentation, of tables of values, which are first my left-hand side and then my right-hand side. And I'm making my tables of ordered pairs. So first tell me the y, and then tell me the value of y squared modulo 5. This is Mathematica command for that. And I want to do that as my y value starts at 0 and ends at 4. I can create this table, and I can even make it look exactly as it did in the set of slides where this is my input and this is my output. I do a similar thing with B here. I make a table of tuples, the first coordinate being the x value and the second coordinate being x cubed minus x plus 1, but again working modulo 5, and do that for all possible x values. And the matrix form just makes it look pretty. And then if I create this empty set x, and I do a little bit of a procedure, I can go through and with a little bit more work and a lot of square brackets for that clunky Mathematica notation for indexing these nested arrays, I can actually go through and do that process I was outlining in the slides of matching up the output value here with the output value here, and then peeling off the input value, and I can append those new ordered pairs to this list X. If I get rid of the matrix forms and run that for loop, and then ask Mathematica for the set X, it gives me exactly the elliptic curve points that I listed in the slides. So something to study if you're feeling pretty decent about your programming skills in Mathematica. You can automate this process, which is really helpful if we are actually working with one of those large primes that we would need in order to do some more authentic elliptic curve cryptography. Now, that's how we go about getting the points that are going to lie on our elliptic curve. How do we go about actually combining things with this binary operation we discussed last time, given that we defined that operation very geometrically, and we've now found the points on our elliptic curve very algebraically? That is, we don't really have a great picture. And the way that we had defined this group operation was with a very visual description. So what that was is we found points A, B, and C that happen to be collinear on the elliptic curve. We'd find points A and B on the curve, draw a line through them, and take C to be that third collinear point. Then we would define A dot B to be the reflection across the x-axis of that point C. The only exception to this was if we happened to choose points that were already opposites across the x-axis, then we would have to define the combination of those two elements to be this new point infinity. We've lost our picture in the creation of this set E. However, it is possible to get a picture back that allows us to do this group operation geometrically if we're willing to remember how to work modulo 5. So let me show you how to take that picture. What I have here is actually a picture of the points that lie on our elliptic curve. Here's the point 0, 1, and then I've also got the point 0, 4 on the curve. So notice what I've done on my x-axis here. I just have 0, 1, 2, 3, 4, the inputs that we had in those tables. But what I've done with my y values is I've started at 0, gone up to 1, 2, and then I've put the value 3 down here, how I would normally think of it as -2, and 4 down here at -1. So 0, 1, 2, 3, 4. And I've then plotted the points that I had in that set E. 0, 1, 0, 4, 1, 1, 1, 4. 3, 0, nothing at 2, remember. 4, 1, 4, 4. And so I do have a picture of an elliptic curve. It's just these points that are plotted in space, but it is still symmetric about the x-axis as long as I put my y values in the plane this way. And so now I can still use that geometric group law if I remember to mod. So let's do an example of this by computing 0, 1.14, these 2 points that I have highlighted right here. If I were to go and draw a line between 0, 1 and 1, 4 in this particular picture, I've gone over 1 unit from 0 to 1, and I've gone down by 2 units. What I want to do next is just sort of extend that line and see when do I next hit one of these red points. That will be my third collinear point, and I'll be able to look at its reflection to define this group operation. So all right, I went over from 0 to 1, over 1 unit and down 2 units. I need to do the same as I move from 1 to 2. I need to go over 1 unit and down 2 units. So go from 3 to 2. So I just wrap around. If I reach the bottom of my picture, just wrap around to the top. Or conversely, if I were to reach the top of my picture and need to go higher, go to the bottom. So this is the next point that I would encounter on the line connecting 0, 1 and 1, 4, this point 2, 2. But I need to keep going because that's the point in space that is on that line, but it's not one of my red points that lie in my elliptic curve. So I go over 1 more unit and down 2 units to the point 3, 0, and that is one of my red points. So this line between these 2 points, 0, 1 and 1, 4, passes through 2, 2 on its way to this third point in the elliptic curve. And so these 3 points are the ones that happen to be collinear and also on the elliptic curve. So if I were to define 0, 1.14, I'd find that third collinear point, 3, 0, and then look at its reflection across the x-axis. And in this example, that's also 3, 0. And that's how I compute my group law. There's also an algebraic way to work with this group law, which really amounts to the same thing. So let's compute the same example, 0, 1.14, and let's just think about slope at this point. If I did a change in y over change in x's type of argument here I could say that the slope that's connecting, the slope of the line connecting these 2 points would be 3, 4 minus 1 over 1 minus 0. And so what I could do is just list out all points that would be on the line connecting 0, 1, and 1, 4. So I'd just say, okay, 0, 1, and 1, 4. The next thing that I do is move over 1 and up by 3. So I'm saying I moved over 1, the 1 becomes a 2, and the 4 goes up by 3 to actually become a 7. But since I'm working mod 5, that 7 becomes a 2. And then I move on, move over 1 from the 2 to a 1, and I take 3 and add it to the 2, so I get a 5. But I'm working mod 5, so that becomes 0, and so on and so forth. And eventually this process will get back to where you started with, 0, 1, 2, 3, 4. Then I would have to wrap around again. Instead of going from 4 to 5, I'd mod the 5 by 5 to get 0. Take the 3, add 3 to it, get 6, mod by 5, get the 1, and I'd be back at the very beginning. So these are all of the points in that sort of 5 by 5 space that would lie on the line connecting 0, 1, and 1, 4. And just as we did with the geometric version, these 2 points lie on my elliptic curve. 2, 2 does not. So I move on, and I would be looking for that third collinear point would be the first value that I find in this list after these first 2 that also happens to belong to E. And that's this point 3, 0. Again, because 3, 0 is its own reflection across the x-axis, it is the case that these 3 points are collinear, and it happens to be the case that 0, 1.14 is just equal to 3, 0.